Hi, welcome to another physics class. In today's lesson, we're going to talk about static electricity. Now, this is a very long topic, so today we're only going to focus on the conceptual part, and we will do the math at another class. Charged objects can interact with each other over a distance. Where do these charges come from? Well, they start from within the atom. And what kind of charges do we have? Well, we always have positive and negative charges. Now, these objects become charged through the transfer of their electrons. And throughout, you might hear the word electrostatics. It's simply the study of forces between these electrical charges. And also the electrostatic force will often get used. This is the attractive or repulsive force between two electrically charged objects. And it's denoted by F elect for electrical force. And it is a non-contact force. Let's go to a quick review from chemistry. Now we've got protons, neutrons, and electrons. So there's a couple of characteristics. Protons are obviously positively charged, neutrons are neutral, and electrons are negatively charged. The locations of these subatoms, the proton is going to be inside the nucleus, neutrons also inside the nucleus, the electron is the one that's outside, and as a result is the one that can move. Mobility, both proton and neutron are tightly bound inside the nucleus. They can't move. The electron, however, they're going to be the outer electrons in which are loosely bound and can easily move. As far as masses goes, all their masses are small, but relative to the three of them, the electron is very small compared to proton and neutron. Proton and neutron will be considered much more massive compared to the electron. Now, my cheesy way of simply remembering the location is pin. Basically, you can't spell in without P and the N. So the P stands for proton, I stands for inside, and N stands for nucleus. So I just think about pin, meaning that the proton and neutron are inside the nucleus. All right, so protons are positively charged particles, and electrons are negative charged particles. One easy way to remember this is to think of the P as profits. Think about it as you have a business and the P is going to be your profits. So obviously those are going to be positive. And the E are going to be your expenses. Those are going to be negative. And this little analogy will come in handy later on. Most objects are at a neutral state, which means that their number of protons is equal to their number of electrons. And as we've already covered, these objects get charged by their transfer of electrons. These are the ones that are in the outer layer. We're going to have uncharged versus charged objects. And the key thing is that even though you might hear the word uncharged, it still means that they both still have positive and negative charges inside them. It's a matter of, are they balanced or are they imbalanced? So an uncharged object has a balance of both charges, meaning an equal number of positive and negative charges, or equal number of protons and equal number of electrons. A charged object has an imbalance of both of these charges, which means it has an unequal amount of positive and negative charges. In this case, their number of protons is not going to be equal to their number of electrons. If you have a positive charge, you have more protons. If you have a negative charge, you have more electrons. If you want to go back to that analogy of the business, if you've got more profits, you're in a positive. If you've got more expenses, you're in the negative. And below, you see the different images as of how balanced, a neutral, and a positively charged or negative charged image will look like. All right, so as we said, it's all about those moving electrons. And I like to use the analogy of profits for positive and expenses for negative. So neutral objects gain electrons. And when you gain electrons, you become negatively charged. Okay, so this is where that analogy comes in handy because most people think that gaining is positive. Now, if you're gaining a lot of expenses, that's a lot of negatives that you're gaining, which means overall you're becoming a negative. If, however, you're losing a lot of expenses, then you're losing all those negative charges, which means now you're in a profit. So hopefully this little analogy will make more sense. Neutral objects gain electrons and they become negatively charged. When neutral objects lose electrons, they become positively charged. All right, I would go ahead and stop this video and try to go ahead and answer these little questions. Basically, you're deciding, are they greater than, equal to, or less than as far as the number of protons to electrons, and why is the case? All right, so when we have a neutral atom, the number of protons equals the number of electrons. The reason for this is because there's no transfer of electrons. When you have a positive ion, the number of protons is greater than the number of electrons. In this case, electrons were lost. So think about it as you have less expenses. If you have less expenses, you're in profit. Therefore, you're in a positive and you have a very happy face. If you have a negative ion, in that case, the number of protons is less than the electrons. So in that case, you gained electrons. In a way, think of it as now you have more expenses. And if you have more expenses for your business, you're going to be in the negative. And if you're in the negative, you're going to have a little sad face. Forces of attraction. Protons and electrons are obviously oppositely charged. So it's basically opposites attract, likes repel. Repel means to push away. So if there are two negatives, they're going to push away. If there are two positives, they're also going to push away. A positive and a negative will attract to each other. Here it is in a diagram format. Like charges repel, opposite charges attract. You may see word questions, you may see diagrams. Be aware on how to answer these questions. Back to Newton's third law. Forces come in pairs. So you're going to have each electrostatic interaction is going to result in a pair of equal in strength and oppositely directed forces. So as you can see, we have objects A and objects B, and each one's going to be applying a force on each other. So with the left arrow on top, that's the force of object B on object A. And on the right one on top, that's the force of object A onto object B. Both of those are positive, so those are repulsive forces. Now, when we come to the bottom, on the bottom left, you have object A is positive and object B is negative. So those are opposites of each other, and they're going to be attracted to each other. So we're going to go ahead and say that the left arrow in the bottom corner is the force of object B onto object A, pulling it closer to each other. And the right arrow on the bottom is the force of object A that is being applied onto object B, causing that to be pulled towards each other. All right, the strength of these forces depends on essentially the amount of charged particles and the distance from each other. Now, this has more to do with the math, and the math portion of this will be in the next class. But you'll see the equation, and it will make much more sense in the next time. All right, there's a couple of rules for charge interaction. We've already discussed 1 and 2. Like charges repel and opposite charges attract. The third one is that any charged object, regardless of whether it's positive or negative, will attract a neutral object. So if you have a positive object with a neutral object, they will be attracted to each other. If you have a negative object, negatively charged object with a neutral object, they will also be attracted to each other. All right, there's differences in types of materials that we have. We call them conductors and insulators. Conductors are objects that have their outer electrons that are not bound to atoms. These outer electrons are able to move freely, and as a result, they allow charges to move easily through them. Examples of these include metals, water, steel, iron, salt solutions. Now, with insulators, these are objects that have all their outer electrons fixed to its atoms. And these outer electrons are held tightly. So as a result, the charge does not move as easily or freely because the whole point of the charge is to be able to transfer through electrons, the movement of electrons. So examples of insulators are plastic, rubber, wool, glass, fabric, paper, styrofoam, and wood, and so on. You're not going to be required to memorize these. However, it's pretty common sense as of what can go ahead and transfer electricity and what cannot. All right, some more differences. So in conductors, if the charge is transferred to an object at a given location, the charge is quickly distributed across the entire surface of the object in an even way. So we see a negative charge rod that is brought towards that object. It touches it, and we have, the negative charge out there at the location is where it touched. But because this is a conductor, those charges are going to go ahead and get evenly distributed towards each other. So all those negative charges are evenly within the surface area. In an insulator, if the charge is transferred to an insulator at a given location, those excess charges will remain at that location of charging. The particles of insulators do not permit the free flow of electrons, and as a result, they do not distribute evenly across the surface. So again, we're bringing a negative charge rod in, we touch a couple of places, and depending on where you touch it, that's where that charge remains there. And because this is an insulator and the electrons are held tightly, they cannot move around and distribute those charges. All right, here's insulators versus conductors. And our white tiles are going to be our conductors, and our gray tiles are going to be our insulators. Now we're bringing basically a negative charge rod over here. And if we look at the top scenario number one, it's touching a conductor, which means it can go ahead and transfer its electrons. Not only does it do that, but then it proceeds to do it an evenly distribution of those negative charges. However, it does not transfer over to the insulator. Now, the negative charge rod in scenario number two touches the insulator, and it is able to transfer it over to the insulator, but because it's an insulator, it will not distribute it anywhere else. And it is held tightly in the same location that it was originally touched in. In the third scenario, we have a conductor followed by an insulator followed by another conductor. So again, you touch that first conductor, the electrons are distributed evenly. However, they will not be distributed towards the insulator, and as a result, cannot go further to the third conductor. And in scenario 4, we have an insulator, and if it is followed by 3 conductors. Now, this purely depends on where you touch. In this case, they touched the middle, which was the conductor, and as a result, all those electrons were transferred over evenly to the 3 conductors. All right, so we just covered the types of materials, and I want you guys to have a little mental break because next up is the ways of charging, and they sound very similar to the ones that we just covered, so I don't want you to get them confused. So we have differences in ways we can charge those materials, being the conductors and insulators, and those methods are going to include, but are not limited to, conduction and induction. So conduction and induction both refer to the different ways that a charged object can cause a charging on a neutral body or a neutral object. Conduction is via contact, so it has to touch. And what happens is both objects, the charged and the previously neutral object, will both share the same amount and the same type of charge. So they either both end up as being positive or both being negative, depending on what the original charged object was. Induction is a process of charging a neutral object without making contact. And in this case, the neutral object becomes oppositely charged of the original charged object. So there's a little subtle difference between the two. And a little cheesy way that I remember it, it's not recommended for everybody, but conduction, you can make contact in duct tape, and the only way that duct tape works is if it makes contact. So that's how I've always remembered it. Induction sounds like introduction, and if you think about it, if somebody says, hey, let me introduce you to so-and-so, then if somebody has to introduce them, you've never made contact with them. So this is how I've just remembered it. It's not recommended for you guys, but if it helps, great. All right, so you're going to see some lab equipment and potentially questions or images of these objects, or they may just mention them. There's the Van de Graaff generator on the left-hand side, and you've got the electroscope. So the images may vary. You may not get the same exact ones, but they all look roughly the same. And of course, do not attempt this at home. However, if you ever see one, make sure that if you ever see a Van de Graaff generator, make sure that you are standing on plastic and you are grounded, as plastic is an insulator. And the main thing with the electroscope is it allows you to figure out charge of an object. And the way that it does is by the gold leaves at the bottom. So by default, if an object is neutral, or if the electroscope itself doesn't have any charge and is neutral, then those gold leaves will be closed. And depending on the charge, if it gets to charge, they will go ahead and separate out and spread apart. All right, so here's how the demonstration and uses of electroscope works. On the left-hand side, we have induction because it's not touching. And on the right-hand side, we have conduction because it is touching. So if you remember the differences between the two, induction, the object that was previously neutral, in this case the electroscope, will end up with the opposite charge of the charged object. So we have the positive rod brought near to the electroscope. It's negative at the very top because it's the opposite charge. And all of those previously positive charges, particles, will go down to the bottom. And when they get down to the bottom, they want to go ahead and separate from each other because like charges repel. So that's why the gold leaves will be extended out. On the right-hand side, we have conduction, in which it's actually touching. So we're going to have a same type of charge and the same amount. So they touch, you have a positive on top, and obviously the charges and particles want to go ahead and push away from each other still, so they're going to try to get some separation. So the positives go down to the bottom, and again, those gold leaves will separate out, indicating that there's a charge. All right, you can also go ahead and figure out with an electroscope if it was previously charged or not, meaning the electroscope itself, did it have a charge or was it neutral? And in this case, in scenario A, at the bottom, we'll see that the legs are already kind of spread. These gold leaves are kind of spread. And, if assuming we can tell by the picture that it's all negative, but looking at it with an object itself in real life, you can't tell. So one way you can tell is by bringing different charged objects around it. Now, in scenario B, you bring a negative rod, and all those negatives are going to be able to repel each other. So that's why you get everything going at the bottom, and the gold leaves separate out further because now there's more of a force. In scenario C, you bring a positive rod close by, and now all the negatives are going to be close to it because this is going to be an induction. And at the very bottom, you have less negatives. So not every single is going to travel, but as a result, the gold leaves are going to get closer to each other. So we can figure out that it was negatively charged because we brought a positive rod close to it and it did induction. Both of those, B and C, are inductions in the bottom. All right, you may see some pictures or you may get word problems, and essentially like there's another picture of an electroscope and you have leaves and so on. So remember, by default, the leaves are supposed to be close to each other if it's a neutral object. In the left-hand side, the two pictures, those are touching, so you've got conduction. And, on the right-hand side, you've got induction. So you're bringing objects, they're brought near to the top, to the knob of that electroscope, but they're not touching it. So be aware of questions that you may see, whether it's word problems or images. They're going to say that it's touching. They're going to say that it was brought near. They're not going to spell out that it's exactly conduction or induction itself. Can you charge two neutral objects? Two neutral objects can become charged if they are rubbed together. And again, only electrons are going to be transferred. Now, the key thing here is that the total charge of both objects is still going to remain the same, meaning the charge before is going to remain a charge afterwards. So charge, just like everything else, is still going to be conserved. The total charge of the objects before and the total charge of the two objects afterwards is still going to be conserved, even though the two objects are going to end up with opposite charges. And this method is called charging by friction. So an example would be if you rub the balloon against your hair. Now, you may have seen examples of this or you may have not, but if you rub a balloon on your hair, and the balloon can become negatively charged. So if that becomes negatively charged, is your hair positively charged, negatively charged, or neutral afterwards? Remember that both of these were considered to be neutral originally, the balloon and your hair. So what happens is, we have different illustrations over here. Remember that electrons get transferred. So both of them are neutral. The rubbing by friction, charging by friction is going to go ahead and cause the negative electrons to be transferred over to the balloon. So there's going to be an excess of negative charge on the balloon. So the overall charge of the balloon is going to be negative. And as a result, because your hair has got rid of all those electrons, it's going to have excessive positive charge. And this is why the two of them are going to be attracted to each other, the balloon and your hair strands are going to be repelling from each other because all of your hair has more of a positive charge. So like charges repel, opposites attract. All right, so charging by friction, there's a couple of key things. One, they both have to be neutral. So the two objects have to be neutral before rubbing against each other. And obviously, for it to be friction, they do have to rub against each other. And the end result is one becomes positive, the other becomes negative. Some of those examples are over there. We already talked about rubbing the balloon against your hair or clothes, socks clinging to each other. You can also rub your socks against the carpet, and you'll notice you have a little zap. This is why, it's important that when you're getting out of your car and you get some gas, that you touch the metal part of your door panel because you've been rubbing against the seat and your clothes. So it's a safe thing to gently touch the metal door panel and to get that charge off yourself, if you will. And this is why it's recommended that when putting gas in your car, that you don't go back and sit in the car itself because there's going to create static friction. So a little safety tip for you guys. But so conduction and induction were both methods where one object was previously charged and one was neutral. In this case, charging by friction, both of them have to be neutral to begin with. All right, so why does a charged rubber balloon stick to the wall? Essentially, the charged balloon becomes polarized, and the attractive electrostatic force between the opposite charges hold the balloon on the wall. So what is polarization? It's the separation of or realignment of electric charges in an insulator. So both the wall and the balloon are insulators. And you get polarization, which basically separates the charges to different sides of that object. And a charge can be induced on insulators by polarization. So that's a key thing to remember. And here's an image of this being in action. Originally, both wood and the balloon are insulators. And by polarization, you can see that all of the charges are kind of separated. So we get all the positives on one end and the negatives on the other end of the same object. And with this, the opposite charges of the protons and the electrons on the wall and the balloon respectively are attracted to each other, whereas the balloon, the two positive sides are going to go ahead and repel each other. So this is an example of polarization. All right, you may have seen some cars or some toys or some things or even balloons that just stick to the wall, and you think about, well, why doesn't gravity take over? Well, that's because the electrostatic force of friction is actually 10 to the 20 times stronger than the force of gravity, if you could believe that. So the electrostatic force is far more stronger than the force of gravity. Now at the bottom, we've got some little constant that's in your formula sheets. We will cover these next class when we go over the math portions. You're not going to be required to memorize these, but it just gives you an idea. The universal gravitation constant, which we've used previously, is 6.67 times 10 to the negative 11, which means you go back 11 spots to the left. So it's really a small number when you think about it. Whereas the electrostatic force constant is 9.0 times 10 to the 9th. So you go 9 times to the right. So that's a huge difference between the two. All right, so rods and electroscopes. You saw images of these previously. You might see some word problems. It might say that a rod touches a neutral electroscope. What happens to the leaves if, the rod is positive, the rod is negative, and the rod is neutral? So you got to read it carefully. It says touches. So in that case, it's conduction. In the bottom examples, you've got one that says it's brought near. And in this case, then it's induction. You also got to understand, this electroscope, is it neutral before or is it charged and so on. So you can tell that based on the images that we've done and based on the information that you have. So you can go ahead and basically do this as practice on your own, and you can go back and check. All right, so I basically provided all these answers for you in previous slides, so I expect you to go back and check on your own. All right, let's go ahead and do this one real quick. You might get a word problem or you might get images. In this case, we've got, a silk and a glass rod, and it rubbed together, and we see that the end result is the silk is negative and the glass rod is positive. So take a few seconds, pause this video, and try to answer some of these questions, and then check to see on the next one if you're right. This would be crucial for you to understand and differentiate between the difference of charges, what gets moved, and overall. All right, so the silk becomes negative. So in this case, the silk gains the electrons from the glass. Now, both of these were previously neutral. So if the glass rod lost its electrons, or you could say it lost all those expenses, and if it lost the expenses, well, the glass rod is now profitable or is positive. And if the silk gained all those electrons or expenses, if you will, now because they've gained all those additional electrons, which are negative, or if you want to call them expenses, they have more bills and so on. So now the silk has become negatively charged. And these two were originally both neutral. So the way that you can charge two neutral objects is by charging by friction. Then that charge on both of these objects afterwards is still the same. So we didn't just magically create or lose any kind of electrons and so on. It's the same amount of electrons exist afterwards as they did previously. Same thing with the protons. All we did here was the electrons were transferred from the glass rod onto the silk. All right, so that basically takes care of the concept portion of electrostatics and static electricity. Hopefully this video was helpful, and join us next time with the math portion of static electricity. Thank you and have a great day.